Hello and welcome to Tuesday's edition of Cracking the Cryptic, where do not adjust your screens. This puzzle on the screen is yesterday's puzzle, 4 lines by Dr. Logic, and a brilliant puzzle it was too. But that is, I'm not going to solve it again in today's video. Mark has sent me a link to a puzzle and asked me to open it live on screen, which is also, which is always quite exciting and is also a little bit daunting, because it normally means the puzzle I'm going to see is either very hard, or the original time I did this was the Miracle Sudoku, which only had two digits in the grid. That's a positive relief nowadays, but yeah, they normally have something interesting about them. So why don't we, without further ado, let me paste this into my browser and let's see what we've got going on. We have got The Special Theory of Relativity by Tobias Brixner, a long rule set. Let's see the grid. Oh, well, the grid looks relatively normal, actually. You've got some cages, some X's in the grid. Let's look at the rules then. So what's going on? Why am I opening this live on screen? Normal Sudoku rules apply. That seems fair enough. Each cage marks a spaceship that is initially at rest in the solver's reference frame, i.e. the grid. Digits may repeat within a spaceship if allowed by other rules. That's already a bit unusual. Normally in cages you can't repeat digits, but apparently we can in spaceships. Each spaceship then accelerates to a high velocity and moves in an orthogonal direction without changing its orientation. The solver must find its new position that is fully inside the grid. Spaceships do not pass through the paths. Spaceships do not pass through the paths or initial/final positions of other spaceships. As a consequence of the special theory of this could get bad now. As a consequence of the special theory of relativity, each moving spaceship is contracted along its direction of motion, i.e. its shape is scaled down in the solver's reference frame. The length of the spaceship at rest divided by the observed length of the spaceship in motion is called Lorentz factor. That looks like the name of somebody. The size is unchanged perpendicular to the direction of motion. The energy of a spaceship is given by the sum of its digits. And the energy of a spaceship in motion is equal to its energy at rest multiplied by the Lorentz factor. Cells connected by an X sum to 10. Well, that's a very prosaic finish to what must be the most daunting rule set I have ever read in a puzzle. So these are spaceships. They move around the grid, or they accelerate to a high velocity, and then we have to find their new positions. They contract when they go fast. The shape of them is scaled down. The length of a spaceship at rest divided by its observed length in motion. So if that one went there very fast, it would shrink. The size is unchanged perpendicular to the direction of motion. Okay, so I think what that means, if that one goes there, so let's try and understand this. I have got things to talk about before we do the puzzle today, but I'm a bit intrigued at just trying to understand these instructions, so forgive me. I never thought I would actually have to do special relativity theory in a video. If you'd asked me a few years ago whether this is something I would ever do, I would have said, why? Why would I ever do that? But no, Mark has other ideas. Let me just try and understand this. So the spaceship moves it shrinks because it's gone up to... Is that because... Right, let me just think about that. So if something goes really fast... No, something's at rest, and then it goes over there. And is it saying that because it's going so fast, if I tried to look at it as it was going that way, it would appear to me it shrinks, because I guess the light that it emits has a speed. But the faster it goes, I can see there would come a point where it would outrace the light it emits. I know, when I was at school, actually, I used to get fascinated. There was it wasn't E equals mc squared. There was another equation of Einstein's. And it all implied that as you approach the speed of light, your mass would increase, and therefore to go that one little scintilla faster, you would get heavier, and therefore you would need even more energy to sort of, achieve that extra tiny burst of speed, and then you would get heavier again. And so that's why you could never quite get to the speed of light, because to do so you would need infinite mass and infinite energy. I don't know if that's true. I think it was to do with E equals mc squared. But it wasn't that equation. I'm sure it wasn't. Anyway, I can't remember. Anyway, so I'm waffling. So this has gone very fast, and it's here in my frame of reference, or however it was described. And then I have to do something about a Lorentz factor. How did that work? The length. Okay, so the length at rest divided by the length in motion, so 2. That would, if it went from 4 to 2, it would be a 2 as my Lorentz factor. Now the size is unchanged perpendicular to the direction of motion. Right. Okay. So what that means is if the spaceship is zooming right to left, its vertical size is not changed. I think that's what that means. So it doesn't get thinner from my perspective. The energy of a spaceship is given by the sum of its digits, and the energy of a spaceship in motion, so that's that one, is equal to its energy at rest multiplied. Oh, so it's higher energy. That's very interesting, actually. So this is wrong. What I've done here is actually wrong. We can say that that's really weird. Does that make sense? So if something is going if something's going very fast, it will have more energy. Okay, but it then shrinks, so it must. So from my perspective, it appears to sort of condense into itself. That feels right. And then it would obviously have more energy at that point. Okay, well, the physics of it, albeit represented in a Sudoku grid, seems a bit mental. No, I get why this has more energy. What's really weird is that from a Sudoku perspective, this is a problem, because I don't want to say anything really that would amount to solving the puzzle, but we're still only introducing the puzzle at the moment. But imagine those were a minimum 1, 2, 3, and 4. That would be 10. If I understand correctly, those two digits should sum up to 10 times by 2, because the Lorentz factor is 2. And that's 20, and I can't make those two squares add up to 20. So it must accelerate slightly less quickly. It mustn't be so shrunk by the time it moves. This is bonkers. Anyway, this is bonkers. I am going to try and do it for you, though, in a moment or two's time. Yes, thank you, Mark, for making me look absolutely, inept in all physicists' minds. Live on camera. Anyway, let's just trot through some other things I wanted to talk about before I started today's puzzle. If you are a patron of the channel over on Patreon, firstly, obviously, thank you so much for supporting us there. But we do have a present for you arriving on the 1st of November, which is really approaching soon. So at 4 p.m. that day, we are releasing a brand new Sudoku hunt from the Skunk Works. It is fantastic. Duality, Deja Vu, the sequel to the original Duality pack. Loads and loads of absolutely wonderful puzzles by some names that are very familiar. So do look out for that. It really is quality stuff. Now, the other thing I wanted to talk about today was the fact that Mark and I are still sort of basking in the glow of being at Stratford upon Avon on Sunday and sharing a live edition of Cracking the Cryptic with so many of you. It was an absolute blast. We've received lots and lots of sort of photographs, and I've got a couple here. I've got this one, which is me with Gabriel and Arturo. So thank you for sending that in. I've got, I need to wish Ben and Laura, especially Laura, a very happy 6th wedding anniversary. And this was quite funny. This happened while we were on stage. I've got a picture. Hang on, here we go. Picture is here. So what happened was it emerged during the episode that it was Ben and Laura's wedding anniversary, and Ben was he was in the doghouse, let's just say, because he had forgotten that it was their wedding anniversary. He had then, when reminded it was their wedding anniversary, got the year wrong. So he thought it was their 5th anniversary. It was their 6th. And I think he's been struggling ever since, and suggested that a shout out on the channel might go some way to allow him back into the real house. So to Ben, and especially to Laura, I hope you enjoyed. I hope you enjoyed Sunday, and I hope you got some chocolate cake. And Ben, my friend, remember your wedding anniversary and how many years it's been. I mean, just tips, just tips, just life hacks. Now, what else? Chloe, it's your birthday today. And I know this because your partner Kieran wrote to us and said that you do watch a lot, and apparently your cat Juno also watches and likes to chase the cursor around the screen. So Chloe, I hope you get some chocolate cake today. And then also to Joe. Joe, you've turned the big 5-0 today. And I had a very nice email from your son TJ and I think wife Jodie, telling us that you solve all the puzzles that appear on the channel before you go to work in the morning. That is some quality solving, my friend. You're a great father of 5, a business owner, an electrical engineer, and very reserved, but with a big heart and an amazing mind. Joe, you sound like an extraordinary person, and I hope you have a great birthday today with some special chocolate cake before, no, I'm not sure when you'll do this puzzle, but I hope the special theory of relativity, well, if you're an engineer, you probably understand it much better than I do. Anyway, with that said and done, let's go back to the puzzle. I was going to say, let's get cracking, but I mean, I don't think I'm going to get much further if I reread the rules. Do have a go. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. So these are all spaceships. Look at that's a weird thing. Hang on, don't I have to... Hang on, each spaceship doesn't... Okay, so none of the spaceships... So it's like one of those games. Do you know the games you used to get when you were a child and you could sort of shuffle the tiles? Mark once made a crossword themed on this. So if I can't move this one, or if I can't move that one, for example, horizontally, because it's going to overlap this one, spaceships do not pass through the paths or initial/final positions of other. That's an initial position of a spaceship. So this one is not allowed to go to the left. So this one is only going up or down. And in going up or down, it shrinks. and then we have to do the Lorentz factor calculations to work out how much energy it then gets. So do we know by how much? Because if it shrinks, it could presumably just become a single cell. And that would be, let's say it went there. So this one zooms here. It's going so fast that from my perspective, it's gone down to a single cell. Then, no, that doesn't work. Okay, I've deduced something. This one, this blue one, goes to a domino. I don't know where the domino is. Although actually there aren't that many opportunities for where it could go. It could go there, there, or there, because it's not allowed to overlap with other spaceships. But it can't go to a single cell, because if it does, the Lorentz factor would be 3. This is, let me just double check I've understood that. The length of a spaceship at rest, 3. 1. Yeah, so it's 3. So this one has to have 3 times the energy of that one. And the minimum those digits could be would be 1, 2, and 3, which add up to 6. So this would have to have at least energy of 18, and I can't write 18 into a square. In fact, it's almost a bit difficult. Let's just say it went there. So now the ratio, oh, I see, it's 1.5, isn't it, effectively? It's 3/2. So whatever I put in there, if this was 1, 2, and 3 again, this would have to add up to 9. Oh, that's actually very easy to do. Yeah, 10, 15, that sort of thing is how it will work. So there's sort of, right, so once we identify where this goes, there is going to be a sort of black dot relationship between the domino, that is the position in the final grid of the highly motional spaceship, and the original position of the spaceship. Now, where else can we look? So, well, let me think. I don't really know where to look. I've got a great big spaceship here. Oh, but it's not allowed to... Oh, I see. Yeah, sorry. I was trying to move it horizontally. And then I was going to say it was going to overlap with itself, but it doesn't overlap. So if I moved it as far as I could to the left, to say here, I was thinking it was going to overlap with itself here, but it doesn't because it shrinks. Right. So perhaps we can work out by how much this one shrinks. So can it... Well, if that one can't shrink to size 1, that one definitely can't. If it shrunk to size 2... then what would we be saying? We would be saying that we have to multiply by 2.5. No, that's ludicrous. Actually, it's no. This is very interesting. So it can't go to be a size 2 spaceship, because if it did, it would. The ratio would be 5/2 times these digits, wouldn't it? Which have a minimum value of 15, the triangular number for 5. 15 times 2.5, which is 5/2, isn't it? Yeah, is a very big number. And it's definitely bigger than I can put into a domino of a Sudoku. Let's just increase it slightly then. If we increase it by 1, then we've got 5/3. Oh, this is getting horrible. Ah! Okay, well, let's just imagine that's 15 again, because that at least is divisible by 3. So if this was a minimum of 15... 5, 20... No, that doesn't work. You can't. This is so I now know. I don't know if this is useful, but I know that this spaceship only accelerates slightly fast, and it eventually goes there. That's where it goes. Because let's say it doesn't, and I absolutely minimize the value of these squares. So this spaceship, this Millennium Falcon here, it goes zooming in this direction quite fast. So from my frame of reference, it looks like it's of size 3 now. Now in that situation, the absolute minimum energy that this spaceship has in it is 15 divided by 3 multiplied by 5, which is 25. That's the minimum value of those squares. Now, the maximum value they can be from Sudoku is 789. That only adds up to 24, so that's not enough. So this spaceship here goes there, and now it's a weird sum though, isn't it? Because now what we've got is 5 over 4 as the Lorentz factor. Oh, but yes, okay, well that's all right. We can do that mathematically, can't we? So we need some, yeah, the row is divisible by 9, so that works. So, yeah, sorry, let me just try and explain what I'm seeing there. So, whatever that, let's say that this value, the value of this cage, or the digits in that cage, is x. Then I know that the value of the energy stroke digits in this cage is x multiplied by 5 over 4. Now, how do we get that into terms that we can understand? Well, one way of rewriting the value of this would be 4x over 4. That's also equal to x, isn't it? So 4x over 4 plus 5x over 4 is 9x over 4. So this row adds up to 9x over 4. Now let me share with you. This is the one part of the video that I actually understand, I think. A secret I share with only my very favourite people. And if you're watching this video, you're definitely one of my favourite people. The secret is that a value of a complete row of a Sudoku is 45, because that is the sum of the digits 1 to 9. So 45, if this is equal to 9x over 4, and I think it is, then what you can see is 45. So I'm trying to do this in my, just trying to explain this in my head, but because the 9x is on the top, I can divide the 45. 45 is divisible by 9 to give 5. Multiplied by that by 4, we get 20. And that is the value of x. So this is 20, and that must be 25 by a process of deduction. Yeah, that's right, isn't it? 5x over 4. Yes, that is exactly right. That's exactly right. So mathematics works, even if... Has the special theory of relativity been proved, or is it still a conjecture? No, it's still I don't know. I think there might be some doubt over whether it's real or not. It's a theory. So... anyway, let's come back to it. So this adds up to 20. That smaller spaceship, although it's the same spaceship just moving very fast, adds up to 25. I have no idea whether that allows me to do anything. I can't think what that allows me to do. I mean, just putting relativity to one side for a moment, that doesn't seem to do anything, does it? I don't see a way of limiting either of those cages or spaceships or whatever we're going to call them. So do we think about... This one's weird, isn't it? Because that has to shrink. Or it has to be scaled down. So, hang on, let me just read the rules again. They don't pass through the other positions. They move in an orthogonal direction. That means they move sort of either side to side or up and down. They don't move diagonally. They accelerate to high velocity. Do not pass. And they are contracted, so its shape is scaled down. I mean, what I want to say is that must go to a sort of triomino. But they don't move. But they don't change size in the perpendicular direction, do they? Oh, I'm not clever enough to know exactly. You see, I feel like if this goes downwards, it should contract, therefore, vertically. And then I couldn't make it work. I think maybe this has to go horizontal. Yeah, maybe it has to go horizontally. Because then at least it can contract. I can scale it down. Because I can change it to be that shape. That is a scaled down version of that. It's got, you know, if you sort of double the size of this, it would gain a side here and then a double length tail. That feels like it might be right. And then it would have the same vertical size, which I like. So if that's right, what then do we know about it? So its Lorentz factor will be 2, I want to say. Now, is that correct? The length of the spaceship, the length of the spaceship 4, is that right? And the length of the spaceship once in motion would be 2, so it would be 2. The energy. So okay. So whatever the constituents of this spaceship, I multiply them by 2, and I put them in another spaceship. But in a much smaller area. The minimum size of those digits, we can repeat digits in cages, can't we, in this puzzle? So if I had 10, 13 times 2 is 20, 26. Oh, right. Okay, that's it. That is it. That's too beautiful for it not to be it. Right, look. This is... Finally, I'm going to get to do things here, because the minimum value I can put into this cage would be if I did exactly that. I minimize the value of these cells in box 1, and then I minimize the value of the cells that are not in box 1 without... So if I make this a 1, 2 pair and make that 1, 2, 3, 4, you can see 13 is the minimum value of blue. Now, that means that the value of the triomino that this becomes when it goes to high speed is 26 at least. Well, how on earth can you achieve 26 in 3 cells? You certainly can't achieve it if the spaceship entirely occupies one box of the puzzle, because these digits would all have to be different and they would have a maximum value of 24. So that's wrong. What you need to do is to repeat digits. Now, the only way you can repeat a digit is at this border. If we were to put the spaceship like that, so it accelerates very quickly to this point, now what you can do, can you make this add up to 26? Well, you can. If you go 998, that is 26. So that is what we have to do, I think. It feels so correct. If you were looking at the stars and you saw this, and the jigsaw, the origami folded into itself in such a beautiful way, you'd be like, I have discovered the secrets of the universe. So now there's a 9 up there by our old friend Sudoku. Einstein didn't have to worry about that. My phone's buzzing. Now, what does this mean? This means that, what were the values of the green and the purple? This one was, oh no, this one's bigger, so it's, no, this one's a bigger spaceship, so it's a lower energy. So that, it's 20 and 25, so this is 20, that one's 25, and it's got a 9 in it. No, that's not useful, so the other 3 digits sum up to 16. Oh, come on. What's this? What does this mean? Ah, this row. Look, Sudoku. I'm going to use Sudoku. That's how desperate I've become. 5, 6, and 7 to place. Oh dear, oh dear. Oh, what did we say about that one? It goes to a domino, doesn't it? Not a single cell. So either a domino there, domino there, domino there. This one, when we did the example, when we were first thinking about the puzzle, this goes, oh. Well, I think that one, it didn't go to a domino, did it? Because the domino would have had to add up to 20. Yeah, this can't shrink. Yeah, when the spaceships are like Millennium Falcon shape, they can't go upwards because they'll get thinner. And I don't know what that can mean in the context of this puzzle. They're going to go side to side and become like shorter. So this one goes to be a size 3 spaceship in either there or there. So these two cells are in this one's bailiwick, or are the result of this one accelerating to high speed. Now that one, so it's always the case that a size 4 Millennium Falcon, oh well that one's forced. Sorry. Oh goodness, my phone's still buzzing. But that must be true, because we worked out a Millennium Falcon couldn't go to become a domino, because the number difference is too great. 1, 2, 3, 4 times 2 is 20. That's too big for a domino. So this is going exactly there. There we go. That's another sort of spaceship relationship that must exist. And therefore, what's the Lorentz factor here? We've got, we put 4 over 3, is that right? Hang on, let me check. The length of the spaceship divided by the length of the spaceship in motion. Yeah, 4 over 3. So these digits should be divisible by 7, I think. Now, if that's true, if these are divisible by 7, and the way I'm getting that is exactly the same way as we did in the first row, but if this is x, what I'm saying is this is 4x over 3. So let's rewrite this as 3x over 3, add it to this, 7x over 3. So what I need to make sure of is that these digits are divisible by 7 in total. Probably. So let's say these were 28. Yeah, that would be okay if that was an 8-9 pair. If these were 35, these would add up to 10. But just using the secret on the row. If these were 42, these would add up to 3. That's very unhelpful. Sorry. So this one is zooming up here, and it must take 3, either those 3 or those 3, but definitely these 2. So that one. You see, if this one went to there, then this one would have to go to there, and we're sort of packing the spaceships in to a fairly defined area. 3s always go to 2s, and that thing, what's that thing doing? That's going to, well, that's going to become a domino. So if it goes, say it went that way, it would just be a domino, wouldn't it? 'Cause it's got to scale down. And by scaling down, in whichever direction it goes, it becomes thinner, and it stays the same height. So if it's going that way, it stays the same height, but becomes thinner. How would I do as a physics teacher? And it becomes more energetic, and its width would seem smaller, so its energy would increase. It would be double, because it would be 2 versus 1. So if that was 10, oh well, this could have repeated digits. Oh, hang on, this has to have repeated digits. Yes, sorry, what I've just noticed there is if that's 1, 2, 3 and 4, and these are all different, it adds up to 10. Let's say it goes there, that domino should add up to 20. That's too big. So this has got to have repeated digits in it. What's the minimum this can be? It can't be 1, 2 pairs, actually, because that would, if this was 1, 2 and this was 1, 2, then these squares couldn't exist. So the minimum of this is 1, 3 pairs, which would be 8. Yeah, that's it. That's it. It's beautiful. Right. So again, the origami is folded in. The proteins are folded into the correct positions, because if this is any higher than 1, 3 pairs, let's make it add up to 1 more than 8. Let's make it add up to 9. then the domino, I'm saying this is going here, I don't know where this is going, but it's going to lead to a domino. Oh, hang on, I've just realised it could go to a domino there. If it scoots downwards, that would have the same effect. But anyway, the same point arises. If it goes here, this domino would have a value of twice 9. Well, that's 18. I can't make a domino add up to 18 in Sudoku, especially not there. But, I mean, double 9 obviously is not possible from a Sudoku perspective. So this can add up to no more than 8. And the only way it can add up to 8 is if it's 1-3 pairs. So that's a 7 or a 9 by the X rule. And, so it's going to go there. Yeah, so what's going to happen? Well, what I think is going to happen, I don't know it goes here, but this adds up to 8, so the domino that results when it does its motion is going to have a value of 16, and that must be a 7-9 pair, which looks very suspicious, doesn't it? That this is 7 or 9. So I think this one's going to do a very short motion that way, shrink and be there, and that's going to be a 7 or a 9. I don't see a problem with that. Oh, but okay, but if this is 1-3 pairs, I can get some digits at the top of the grid, because that's a 2 now. So that's 2, that's 1, that's 2, that's 1. I love this. That's 4, that's 3. This is very, very original and strange, but really, really rather wonderful. Right, look at this X domino now. It can't have an odd digit on it, because it would be 7, 3 or 1, 9. Both of which are ruled out. So this is even digits. It's 2, 8 or 4, 6. There's a 3 in the purple cage now, in the top row. Because this 3, obviously none of those green ones can be 3. That can't be a 3 because of this. So that cage, which added up to, I'm going to get this wrong again, aren't I? It's not 20, it's the smaller one, it's 20. This was 25, this was 20. Yeah, that's good. That's good. So this, we've proved this cage has 1, 2 and 3 in it by Sudoku logic. But we know it adds up to 20, so 1, 2 and 3 add up to 6. So the other two digits add up to 14 and don't involve a 9. So this must be 1, 2, 3, 6, 8 exactly. Let's just put that in. 1, 2, 3, 6, 8. I know the 1 and the 2 are not there. And the 8. The 8 isn't here either. So that's a 3, 6 pair, which means these are not 3, 6. 1, 2, 8. That doesn't affect those. What are those squares then? 4, 5, 7. Bobbins. Okay, what about... Oh, I see. So these are 4, 5s. Oh, well, there's 4 in the top row. That's got to go here. Sorry, that's an obvious point. So these are 5, 7, and 9. I want to just check the maths. I mean, it must work, surely. 5, 7, and 9 is 25. That's right. That's the number we were aiming for. Now, if this is 5, 7, 9, that's a 6 now. So that's an 8. So these squares are 3, 4, 6. Ah, this is great. 3, 4, 6. That's not 6. There's 5, 7 here, 5, 7 here, 5, 7 up there. Now, is it that one? I don't know. Is it? Hang on now. Can we do these 1, 3 pairs now? No, this looks like to me... Well, this is going to be disambiguated only by this, isn't it? That's otherwise a deadly pattern. I'm not sure really where to look, actually. Maybe it is that one. That one? Yeah, okay, size 4s we know have a relationship with 7, don't they? Because... because that's what we worked out here. We worked out the Lorentz factor was 4x over 3, or 4 over 3. So the sum of the of the original spaceship and the spaceship in motion was 7x over 3, which means I want those digits to add up to a multiple of 7 so that I can make x an integer. Now, so yeah, okay, so the outies, by which, let me explain what I mean by outie. Let's just say that this spaceship, running out of colours here, that spaceship goes there. It's only got 2 positions it can go in. It either goes there or it goes there. Let's just suggest it goes here. Let me pick a colour. I'm going to have to reuse colour. I'm going to say this one shoots upwards and goes here. Now, I think that because I want these to add to a multiple of 7, the outies in the column, the ones that aren't in the spaceships, are going to be the remainder. So if we think about numbers like 4 times 7 is 28. That wouldn't work. No, it certainly wouldn't. It wouldn't work with this spaceship. It might actually. That might work if I move the spaceship down there, and say it moves to here. Then it would. That would work. That's probably right, because now if I make that a 9, these squares would add up to 28, which we'd have to split into 12 and 16. And then this one would be, that would be the 16, I think. That would be the 12. And this would be an 8-9 pair at the top of the grid. To make sure the whole column added up. But it's not necessarily like that, because what you could have is that green and purple add up to 35. These 2 squares would then add up to 10, wouldn't they? And then what did I work out? What was the value of the Bobbinsy stuff? The spaceships. So if we're at 35, then x is 5. Hang on, no. What? No. X. Well, the number we're looking at is 5. We multiply 5 by 3, so 15 and 20 are the sizes of the spaceship, and the smaller one has the bigger value. So that doesn't work, actually. That definitely doesn't work. So if, okay, let me concentrate on this. So if the spaceship moves to here, what are the possible values of all this? Because this cannot add up to 35. Because this should add up to 20, and that would make that another 6. If these added up to 42, these would be a 1-2 pair. They're clearly not that. So the only thing I have to rule out is, well, it can't work, can it? If these 2 add up to 20. Well, if these add up to 17, that would be a 9 and that would be an 8. And I'd repeat the 8. 4. Yeah. Another way of seeing that is that this would be a 16 cage, that would be a 12 cage, so this should be a 2 by mathematics, and a 12 cage in 4 cells needs another 2 in it. So it definitely doesn't work for 2 different mathematical reasons. So this is not the spaceship we're looking for. The spaceship we're looking for is that spaceship. And now we know the outies here add up to either, well, they have to add up to 17, because this cannot add up to 10. This is too big. So that's a 9. Okay, so we've got 5, 7 pairs all over the place. This spaceship, let me just double check my maths on this. So yeah, this spaceship has to add up to 16, doesn't it? So doesn't that have to be a 3, 7 pair? It has to add up to 10, and it's not 4, 6, 2, 8 or 1, 9. And these squares add up to 12, and they're going to be 1, 2, 4 and 5. And there's no 1 in any of those squares. So this square here is a 1. all of these, right, we've got 1, 2, 3, 4, and 5 used up in box 7. So these are all, whoopsie, whoopsie, whoopsie. These are all big digits, 6, 7s, 8s, and 9s. That's slightly overzealous on the pencil marking, I think. Oh, well, we're going to look at this now, aren't we? Probably. Oh, what about that one? What's that do? Oh, this is great. No, I'm going to look at that one. Because that one has to move there. That's the only way it can move. Because it's a Millennium Falcon shape. And we worked out Millennium Falcon shapes move sideways, like that. And they have to go into size 3 regions. These can't add up to 17, and they can't add up to 3, so they must add up to 10. So this square is 3 or 7, and the mathematics of this row is a 20 cage and a 15 cage, and that is the 20 cage, and it doesn't have a 7 in it, so it's not 5, 7, 8. So it must have a 9 in it. A 3-cell cage in Sudoku with different digits in it that doesn't contain a 9 can only be made up in one way if it adds up to 20. It's got to be 5, 7, 8, and it can't be. So it must have a 9 in it. It doesn't actually look useful. But it's got a 9 in it, and then 2 other digits that add up to 11, which are not 3, 8, or 4, 7, or 2, 9. So they are 5, 6. So this cage is known. This is 5, 6, 9. These squares are now 1, 2, 8, and 4. Now, let's check the mathematics on this. 15. Yeah, 15, 20. The small cage has the bigger energy, so it has the bigger number. This is not 8 by Sudoku. This is not 1 by Sudoku. Now, what does this mean? I don't know, but I'm quite excited by it. No, I really don't know, actually. I might have to, I think I'm going to have to think about that digit, but let me just think about this for a moment or two. See, that's going to be a 2, isn't it? That's my prediction. It's a 2 or a 9, because we know the outies in a Millennium Falcon row, which is this one, this column, and this row, i.e. where a 4 becomes a 3. We know we're looking for multiples of 7 for the inner stripe. So the outies are either adding up to 17, 10, or 3. These can't add up to 17. They can add up to 10, probably. And they can add up to 3, probably. Now. Okay. So if that's a 9, then this is 20, and it would have to be that 5, 7, 8 that we were thinking about before. Oh, I'm not sure. If this is 2, how does the mathematics work if we're heading for 42? Then we're looking at 18 and 24. Oh, that's nearly impossible. That's going to be right. That's going to be right. Because if this had to add up to 24, it would be 987, and we could place all the digits because of Sudoku. So I think that's going to be correct. I think this is going to end up being a 2. I don't know how we prove it, but that's what I think will happen. And these would be 3, 4, 5, 6. Ah, bother. Right, how do we do this then? Well, okay, let's do Sudoku. If we're resorting to nonsenses, where's 2 and 4 in this column? They're there by Sudoku. Does that do anything for us or not? I don't know, actually. So 5, 6. So 8 is definitely in one of those squares. So that isn't an 8 for what that's worth, which is probably not much. So 8 is in a domino down here. I don't know what to do. Is it one of these other ones? We know these are 3s becoming 2s, don't we? 3s becoming 2s, so they're in a 1.5 relationship in terms of energy. I mean, that just feels horrifically open-ended, I have to say. All I've got to make sure... Just got to make sure they're even, don't I? So they can be divided by 2 and then multiplied by 3. If I knew the parity of this, it would be helpful. Then I could at least identify this one, think about parity a little bit in that context. Oh, I'm sorry, I'm now stuck. I don't know what to do. Where should we... Where do I look now? I don't know. We could look at... Oh, dear, dear, dear. I don't know. Is it some sort of Sudoku nonsense? I don't think it can be, but maybe there's a way. It's not this X, is it, somehow? Is that doing some magic that I don't appreciate? There's no problem with moving through an X, is there, with my spaceship? I don't think it said I couldn't move through an X. No, it doesn't say that. It just says we can't move through the final or initial or paths of any other spaceships. What's the paths thing doing? Oh, I see. I'd never even thought of that. Okay, what if that spaceship... Oh, that's... Oh, that could... I've actually had an interesting thought there. But what if that spaceship went up there? It could have done that absent the rule that says it can't move through the paths of other spaceships, or I suppose the initial positions of them. So this, yes, okay, this is what I've missed. I forgot that we know where this one, well, we don't know where it goes, but we know that it has to find a home which is a 7-9 domino. They can't be there. That would break. They can't be here because these are even. Oh, this is beautiful. So they're either exactly there, or could they be there? That was the thing I noticed before, actually. Or could they be there? Oh, no. No! I don't know, actually. How am I meant to do that? I think here looks possible, perhaps even likely. 7, 9, 6, 8. Don't see a problem with that. I mean, if there is one. 5 here, 6 here. Okay, but then it could, I think, go down here. That would be really sneaky, wouldn't it? And this is a 7, 9 pair. And this would be 6, 8. Don't see a problem there. Or it could be a sideways easterly movement, and this could be a 7, 9 pair. But I think if it does go east, that is the only possibility. So the final domino of 7 9linesses end up looking like that. Oh, and I do wonder whether there's one of those that's just, you know, illegal for some reason. I don't know. That's very peculiar, isn't it? So, 2, 3, so 6, 5, 6, 8, 9 here. Actually, look, I'm going to resort to heavy pencil marking and I hope I spot something. I don't know how to do it. What? Should we have a look at this row again? What was the mathematics of this row? If this was 9, then these add up to 35. One of them is, this one is 20. And this one is 15, isn't it? It wouldn't have a 1 in it, actually. That would be at least a 5. That's very difficult to do. In fact, is that, can you do that? That could be it. Wow, that's very difficult. Right. Maybe there's a different way of seeing this, actually. Yeah, maybe there is. Because if this is 9, this is 5, 7, 8, isn't it? Oh, yeah. This is lovely. Right. Okay, let's think about it a different way entirely, just so we can understand it together. So, the choices here are twofold, I think. The first choice is that this is 9, in which case the mathematics of this requires these to add up to 20, and they must therefore, because this is 9, be 5, 7, 8. So what I want to note from that is that in these cells we've definitely used up 7, 8 and 9 in that instance. Remember that if this is 2, these have to add up to 24 and be 7, 8, 9 themselves then. So 7, 8 and 9 are always, in row 6, they are always in those 4 squares. Now, what does that mean? Well, it means it means 8 only has 1 home, actually. That's one thing it means. That's certainly not 9. 9 is in these 2 squares, so this isn't 9. 9 is definitely in this domino, because it can't be in these squares. 9 is in these squares, so 9 is in those squares. Is this going to get us anywhere or not? I'm unsure at the moment, but I'm trying hard to work out what it might mean. Yeah, oh, hang on, this is... Oh, that's beautiful. Oh, this is sick. This is really clever, actually. Right, we worked out that 7, 8 and 9 were in these 4 squares. Where's 8? And I don't know the answer to that, but it's actually, look, in that domino there. So that takes 8 out of these squares. It places 8 in the middle box. It places 8 down here. That's going to take out that domino. That's 8. Oh, that's so beautiful as well. Oh my goodness me, this is sensationally clever, this puzzle. It is sensationally clever, because now let's revisit where this spaceship disappears off to. We know it finds a 7-9 pair. It can't be here. It can't be here. It can't go through other spaceships, and it can't be there, or there. So nori nori, it goes there. That is where this spaceship disappears off to. That is the only place it can get a 7-9 pair. That fixes this digit 5, fixes that digit 7. That's now a 9. So so this is 5 or 6 by Sudoku. Yeah, we're putting all sorts of pressure on this cage now. We might be able to do something with that. That was what was starting me to think originally about how to think about these digits. But anyway, let's just see if we can do more. I've got a 7-9 pair here. Is that useful? 8 is in one of those 3. It'd be very useful if we could get it onto the dot, wouldn't it? Sorry, on the X. Then we would know this was 2 and 8. Are we allowed to do that for some reason that I'm not understanding? I don't know. I don't know yet. Now, so we know, don't we, that 7, 8 and 9 live in these squares somehow, some way. So 7 is in one of those 3 squares. 6. Oh, I see. Look, where's 6 in this box? I don't know the answer, but it's in this domino. So that's getting me a 6 up here and a 3 here. So 3 is now in one of those 2 squares. 1 is in one of those 3 squares. hands. I'm not sure what to do with that. 5 is in one of these 3 squares. And can we now do more magic down here? If this was 9, didn't I work out that had to be... Oh, which way round did it go? I can't remember now. Yeah, that doesn't work. If this is 9, what we worked out is that this adds up to 20, and that adds up to 15. And that means these two... Well, let's look at this. That proves it's impossible. These would have to add up to 4. There's no way. So this is in fact 2. So that's 9. That's 8. That's 7. Oh, I thought we were going to be able to go further. This is 4. This is 2. This is 3. I've not put 3 in the row. That's the only reason I got that. These squares, look, seem to have to be a 1. Oh, 2. Where's 2 in the box? 2's got to go here. So that's all fixed. 1 goes here now. 4 goes here. Suddenly we're doing really well. This is now a something. Technical term. No, I was going to say 7. That's not right, is it? 2 is what it is. Okay, these are 4, 5, and 6. But we know that's not 6, I think, from this. Okay, so have we now... That's not 2. 4, 5 pair in the bottom row. Okay, have we now... I don't know what to look at. Okay, well now we can... No, we can't. We don't know how the 3 and the 7 break down, do we? So perhaps we have to look at these digits then. We know these digits are 3, 5, 6, and 7. Now, do we know any more than that? Didn't we work out that this needed to be even? Am I going crazy? I thought I did think that needed to be even, because its Lorentz factor is going to be 3 over 2. So if this was odd, it wouldn't work. The other cage we would create couldn't add up to an integer. So if this needs to be even, this needs to be an odd number, doesn't it, to sort of match up with this? And that's very annoying, because all it does is take 6 out. Bother. Oh, that's disappointing. So 6 is in one of those squares. There is a 3, 5, 7 triple in that little coterie of digits, for what that's worth. That's not a 2 in the corner. Okay, let's minimize that. That would give us 10. So the other cage we would need is a 15 cage. There can't be a 15 cage. Can that be a 15 cage? Or can that be a 15 cage? Oh, actually, look, 9 is down there, I'm noticing. Well, that's very possible. That could be 9, 6 immediately. Bother. Right. That's not 8. Oh, that's big. That's big. Where's 8 in this row? And the answer is on this X. So this is 2, 8. Now, although I know the order. So that's 2, that's 8. That's 1 in the corner. This is 8. This is 2. Come on. Now, what's it doing down here then? It's placing 2 here. So I haven't put, this is 4, 5, or 6. No, that's not what I wanted at all. Oh, okay. I wonder. It's quite difficult, but the problem is as well, we don't know, do we? We know that, we do know there's a 3 in here, actually, looking at this 3, 5, 7 triple. So there is no 3 there. So, I probably missed a rule or something. How are we going to do this? It does feel like it's this that must resolve things, doesn't it? Or at least that's what it feels like to me. Have I got every 8 in the grid? The answer to that is apparently yes, if I got all the 2's in the grid. Also, yes, 1's in the grid. Oh no, we haven't done very well with 1's. Well, although we do know one of those is a 1. Does that feel... If that was a 1, this would add up to quite a small number. If that was a 1, this would need to be 5 by our even logic. So this would add up to 8, and we'd have to find a 12 cage. No, we wouldn't. Yes, we would. A 12 cage there, not there. Not... Oh, 5, 7. No, because that would overlap. 12 cage here, perhaps. 9, 3, maybe? Oh, bobbins, I don't know. Right, come on, Simon. How do we figure this out? Is there an obvious way of resolving what we've got going on in the grid? And I can hear a cacophony of people in the future saying, if only you understood Lorentz factors properly, Simon, you wouldn't be such a muppet. No! Maybe this can't be too big. I haven't thought about that. What's that? Yeah, actually that is a good thought. It can't add up to 12 even, can it? If it adds up to 12, given we're multiplying it by 1.5, we get 18, and that's too big for a domino. So this adds up to less than 12. And that means you can't put 7 in it. That's beautiful again. If this had 7 in it, given we're adding 2 and at least 3, we're getting to 12 and we can't get to 12. That's the whole point. Oh, Simon. So this has to be 3, 5, and I know the order. 5, 7. These are not 5 anymore, so that does do the 7 and the 3. Okay. Right. And we're going to be able to hunt for spaceships that... or this spaceship and where it lives in the final world. Well, let's do that now. So this is now adding up to 10. So we need a 15 cage, which is definitely not there. So it's down here somewhere. It can't be 8, 7. 8, 7, there's no 7 available. So it's the bottom, and that involves a 9. So it's 9 and 6 is the spaceship that sort of, that this one becomes. Now, okay, that gives me a 6, 7, 9 triple in the bottom row. So this is a 1, 3 pair, I want to say. That's interesting, because 1 and 3 is most certainly odd. So this needs to be odd to ensure this is even overall. That is something we have at least learnt. That means this is 5, this is 4. This is not 5 anymore. Oh, in fact, that is 4, and that's 6 by a small arcane process known as Sudoku. That's 4, that's 1, that's 1, that's 3. We're going to... Oh, we've got the same. We've got the same thing. That's going to be a 7. Oh, no, it could be a 6. I don't know. I don't quite know what's going on. But hopefully we're going to get to a solution now. Let's see. So 6 here, 7 here. We have not put 5 and 7 into this row. 7, 9. 9. So that unwinds this deadly pattern. This becomes 6, 7. That unwinds the 6, 9 at the bottom. And now, I'd love it if this was some sort of deadly pattern. And it has to be resolved by where this spaceship goes. So that spaceship needs a 15 in its row. Where does it get it? You can see it's going to be here. That's the only place it can get it now. So so this spaceship, let's pick the right colour. What do we think the right colour is? I don't know. Red. I've not used red. That's lovely. So this small Millennium Falcon goes there. Has quite a lot of energy. Must be worth 15. This is 6. That's a 7. Whoops, that's a 5. So that's a 6. That's a 5. That's a 6. We need a 9 here. And that should be a 5. And that's the puzzle. That is the puzzle solved. Isn't that fantastic? Good grief. We have solved the special theory of relativity. Probably. Let's see. Yes. Solve counter 1. I'm the only one who's done it. Oh, that's fantastic. Tobias Brixner, Take a Bow. What a strange and wonderful puzzle. Very, very odd and really, really imaginative. I mean, to think that you could create a Sudoku involving Lorentz factors and special relativity. And, well, I have no idea how accurate the physics of this is. I will rely on, I mean, there are an immense number of very clever people who watch Cracking the Cryptic who will either scoff at me mightily or correct me gently, please. Anyway, Tobias, take a bow. Let me know in the comments how you got on. I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.